Welcome to breakout session BRKDCT 2081, Cisco FabricPath Technology and Design. I hope you're having a good time at CiscoLive. When did you guys arrive? Yesterday? The day before? Okay. Wonderful. So my name is Elior Hakimov. I've been with Cisco for 7 years in various engineering roles, and for the last 3 years, I've been part of the product management team in a data center and enterprise switching group. So my primary focus in the business unit is dealing with the fabric technologies, namely FabricPath, Fabric Extender, and it's been my key focus for the last 2 years. I'm also working on layer 4 to 7 services, firewalls, and load balancers integration with the fabric. And today, I would like to share some of the findings we see our customers are, how they're using FabricPath, what are some of the things that they like us as a company, as a business unit, pay attention to. So here's the session abstract to remind you why you're here. But really, the goal of the session is to give you conceptual, provide you understanding of a conceptual and technical understanding of the Cisco FabricPath forwarding, data plane, control plane, and also show you some of the network design and best practices. If you are interested in getting more details in terms of how do you operate and troubleshoot Cisco FabricPath, I recommend checking out the related session, BRKDCT 3313. There you will be able to get some more information on how you can operate and troubleshoot Cisco FabricPath. And without further ado, here's the agenda. The introduction is really high level, couple of slides just to level set the audience. Then we will go into the Cisco FabricPath forwarding concepts, data plane, control plane. Namely, we will talk about unicast and multicast and how control plane establishes the forwarding states for the data plane. Then we will talk about how all of that technology and conceptual notions trickle down to specific designs. Who had been with Cisco to this session before? Raise your hands. Okay, we have 100% new attendees. Wonderful. And then we will finish off with the key takeaways. So, introduction to FabricPath. Before I start, how many of present in the audience have already deployed FabricPath? All right, I'll say about 20%. What about those who are about to deploy or are in the planning stage? Okay, a lot more, about 30%. Wonderful. So those who are in the planning stage, the next slide would be especially interesting because it's 2015 today. So why FabricPath? Why FabricPath in 2015? And to answer that question, I need to go into a little bit of a discussion of data center technology evolution. So we started off with the FabricPath, with the spanning tree protocol for the layer 2 networks, and our customers were building, it was working fine. But then some of the drawbacks of spanning trees started becoming very prominent and very bothering. So we evolved technology with VPC, Virtual Port Channel. We further evolved the technology at the access layer in terms of the management by introducing Fabric Extender. Now you can have multiple devices at the access layer managed by one, let's say, top of rack or end of row. And that brought a lot of attention, and our customers deployed this in tremendous quantities. Fabric Extenders is very popular technology. Then what we did, we introduced FabricPath, which is the key and the focus for this session today. But then you may ask, hang on a second, FabricPath in 2015, we have things like ACI, we have things like VXLAN, EVPN, so really, why FabricPath? The simplest answer is here. So technologies like ACI, they solve a lot of problems all at the same time on many different aspects. Now, that requires teamwork from network teams, from storage, from services, from application guys, all together. And we have a lot of customers who are successfully working in that direction. And some customers are in various stages of readiness. Some are closer to getting to the ACI or VXLAN, and some others are further out. And there are several reasons for that. First of all, they already have certain operational standards, operational best practices. They are not changing as of yet, but they will when they get to the ACI or VXLAN. Right? That's one. And the other is layer 2 simply works for them. Layer 2 worked for them, and it works for them. However, they are looking into incremental improvements and changes to technology that drives the fabric so that they can keep using the layer 2 in the new environment. For example, large network and spanning tree domain doesn't quite correlate very well. So they need some incremental changes. FabricPath is that technology that can give you this level of incremental changes, immediate benefits, as we will see further in the presentation. So before I go any further, I would like to mention that we in the product management team and in development have multiple dedicated people dedicated for FabricPath, marketing, engineering, as well as the development. So FabricPath, layer 2. Why layer 2? Why layer 2 in data center? Well, if you look at some of the largest, and I mean very massive data centers in the world, they're not running layer 2. They're running layer 3 in the fabric. And why? Well, because they have extremely tight control over entire application stack. What applications they're running in the network? Every single piece of network intelligence that exists in the fabric, they can bring it in and have a very tight control over it. On the other hand, enterprises, various enterprises, but most typical enterprises, do not have that level of flexibility and control over how they bring in the intelligence into the fabric, into the application, because they just need to use whatever applications are there, had been there for the last many years. So certain protocols, certain applications work only on layer 2, or some others work much better when they are layer 2 adjacent when compared to layer 3 hop away. Now, also the layer 2 provides you plug and play capabilities. You do not need to provision MAC address. You just plug in device, host, workload, or virtual machine, or appliance into the network, and it just shows up there because of the nature, the flood and learn nature of Ethernet and layer 2. Now, okay. So, and one of the most popular reasons why layer 2 had been and is still up to this day popular is virtual machine mobility. Now, why virtual machine mobility requires layer 2 adjacency? In many cases, it's because our virtual machine needs to retain the default gateway MAC and the default gateway IP address when it moves from one place to the other place. Now, there's also some family of applications that do not move. However, they are clusters. And when they're clustering, they need to retain their TCP session uninterrupted. And what facilitates that is the layer 2 adjacency. All right, so the typical design that we saw very large number of our customers implement is this. We have pods, and all the layer 2 benefits that I listed on the previous screen are contained and scoped to a given pod. So we can have multiple VLANs within a given pod, but we cannot span those VLANs across pods because we are terminating those VLANs on the layer 2, layer 3 boundary at the aggregation layer. You can route between them through the core, but then there is no concept of any VLAN anywhere here. So to achieve that and fix that, some customers with, I have to say this, with various levels of success, try to bring in the spanning tree from the aggregation all the way up to the core. And you can imagine what happens if you have a very large number of switches in the spanning tree network. So what are the problems? What are the problems associated with that? I'm sure many of you will have some stories to share, but to refine and put something on the paper here, we have the following problems. Local problems in one part of the network will become massive problems in the entire layer 2 fabric. Why? For example, if we have spanning tree link failure, what happens? If link failure triggers the topology change, then TCN, topology change notification, it's a spanning tree message, is sent throughout the fabric, And one very nasty nature of that CCN, it flushes MAC address tables. So if one thing somewhere in one part of the network changes topology, the whole network is flushing the MAC address tables. Not a good thing. Now, another thing is, because it's a spanning tree, it calculates tree topology. So spanning tree is rooted at some switch, and then from that root, we have branches through the network. So what that means is, if you have multiple paths within the network, you cannot use them because those redundant paths are blocked by the spanning tree. And in continuation of the same tree topology, if you have two adjacent switches and you need to communicate between them, and there happens to be a link that directly connects them, you still can't do that because the spanning tree is blocking that port. Also, if you have 20 switches or 200 switches in the network, and they're built using just plain spanning tree or layer 2, you will have to have all of the MAC addresses of every single workload and virtual machine on all of the switches. That's the nature of flood and learn broadcast Ethernet. So what can we do? We would like to take the best of the switching world, which is plug and play, easy provisioning and configuration, and take the best of the layer 3 world, which is stability and scalability. Remember, I mentioned some of the massive data centers are built using layer 3. We want to bring in some of that into the layer 2 fabrics. Then also, we would like to share, be able to leverage multiple paths within the network, so ECMP. And of course, routing protocols are very well known for fast convergence. As a result, if we combine the two, we get the FabricPath. So why FabricPath? This slide really presents the FabricPath benefits in contrast to spanning tree protocol. So with FabricPath, you can either drastically reduce or completely eliminate spanning tree from the network. Now, the workloads, hosts, they attach at the edge of the network, edge of the spanning tree network at leaf nodes. While we recognize that if you need to plug in your existing spanning tree domain, you can do that. We give you knobs and dials to do that. Or maybe you would like to have your spanning tree as a central fabric, and your spanning tree domains are interconnected through FabricPath. If you choose to do that, we also can give you knobs and dials, and we accumulated a lot of best practices how to do it. We have published numerous white papers on that, and we can guide you through how to do it the best way. Now, better scalability and stability. Because we use SPF, shortest path first protocol, as an underlay protocol for the FabricPath, we can achieve that fast convergence and full topology visibility. So just to emphasize this, we are using SPF protocol, FabricPath IS to IS. Now, it creates the whole topology view, and then it can calculate the shortest path or most optimal path within the network. Also, let me just add something about the convergence. We have ability by the way, this FabricPath technology works on the 2 series of Nexus switches. Those are Nexus 5000 and Nexus 7000. And also, you can use Fabric Extender if you decide to do so. Now, on the Nexus 5000 today, in terms of the convergence, the quick convergence, we have a protocol called BFD, bidirectional failure detection. This had been asked by many customers who are deploying large FabricPath networks. We can give you that today. On the Nexus 7000, the code that has the BFD capability is about to be released very soon. I actually need to check if it's been published already or not, but it will be out very soon. So we will support BFD there. Now, to continue the topic here, it's very simple to configure. You really need few lines of configuration to get the FabricPath up and running in your network. And also, because we have full topology view, using the link state protocol, the shortest path first SPF protocol, FabricPath ISIS, we know that if we have multiple equal cost paths, we can leverage them in parallel. So we can use the same thing that layer 3 fabrics use, ECMP. Great. And also, last but not the least, which is important to some customers, and maybe to lesser degree to some others, deterministic behavior in terms of bandwidth and latency with typical design. So our typical design, what we propose in terms of the FabricPath, is a two-tier topology where you have leaf nodes and you have spine nodes. In this case, you have ability to have very deterministic latency from any node to any node. All right. Now let me pause for a second and ask any questions. All right. I need to remind you that we have Question Manager on duty, one of our technical marketing engineers, who will be ready to answer any of your questions in that online app. You can either go through your application and ask questions there, or you can ask questions going through the web page. Oh, by the way, if you have any questions today and you didn't ask them during the presentation, you can ask them later, and I will personally follow up to tonight, make sure that those questions are answered. Now, finally, we have something we can call VLAN, any VLAN anywhere. What does that mean? Remember the traditional slide I showed you of the traditional network? We have pods, and VLANs, set of VLANs are only limited to that pod. Now with FabricPath, we have access layer, wide access layer, where any VLAN can exist on any one of those switches, and workloads can maintain layer 2 adjacency through the fabric. All right. Forwarding. Here we will talk about some of the Cisco FabricPath control plane and the data plane in terms of unicast and multicast, and how we facilitate work and drive the layer 2 network in FabricPath. All right, so the FabricPath control plane really consists of three portions. First of all, it's the routing table. Then we have multi-destination trees, and we have mroute tables. What is the routing table? Because we use FabricPath ISIS link state protocol, we are establishing direct adjacencies between any two FabricPath nodes, and then exchanging and flooding information throughout the network to recognize and calculate the topology. As a result, the routing table will have a list of routes from any given switch in the network, FabricPath switch, to any other switch in the network. We use switch IDs for routing, and I will talk a little bit more in details a little later. Now, the multi-destination trees, why do we need them? Remember, in spanning tree, you have tree that is built to avoid loops in the network. And that's done because if, for example, you have a broadcast traffic, it goes through the network, and there's no tree or predefined path how this broadcast traffic can go through, it may start looping around and oversaturate network, so it's a meltdown. Here, we have multi-destination trees. So we built trees, and we will see in details on the next few slides, for that exact same purpose, to constrain sort of a broadcast traffic to a tree topology. And finally, we have mroute table. There are two components that go into mroute table. It's the IGMP snooping, and we also have FabricPath ISIS expresses interest from any given switch to any other given switch, interest in particular multicast group. All right, let's go one by one through these components of the control plane. So, in FabricPath, is this MAC-based routing? And the answer is no, it's not. The routing in FabricPath happens based on the switch ID. So any switch maintains the routing table, and it says, all right, if I want to go to this particular MAC, I need to go to that particular switch ID. So inside the FabricPath fabric itself, on spine nodes, we switch based on the switch ID. We do not look into MAC address. So the routing table contains shortest path from any given node to any other node. And if there are multiple paths throughout the network, we can leverage them. So let's have a look at the routing table from behalf of switch S100 on the left bottom side. Here you see that S10 switch 10 is directly attached, and that's why we have shortest path, which is 1 hop away. It's not even 1 hop away, it's directly adjacent. And the egress interface for that is link 1. Now, on the other hand, if we look at the switch 300, we have 4 available paths. So if any traffic needs to go to switch 300, we can leverage one of those available paths using ECMP, equal cost multipathing. So this is what routing table looks like. You may see some resemblance to IP layer 3 routing table. Just the exception here is we do not have IP prefixes here. Instead, we have switches. We have switch IDs. And really, let's say for switch 10 that you saw on the previous slide, we have one egress interface, port channel 10. And if you notice here, we also have administrative distance and metric. So we do calculate best path cost metric. When we do take that in consideration when calculating the best path. And also on the bottom, you see the switch ID 300 is available through 4 port channels. Any questions? Okay. Question. How ECMP load sharing decisions are made? We perform ECMP load sharing just like we do it in IP routing, where we use some values, some information contained in the header of the frame. So for example, if my frame is coming in and I need to figure out, I have 4 available equal cost paths. Which one of the paths do I need to pick? I take the information from the frame header itself, I push it through some function, and we'll call it a hash function, and that gives me some pointer. It says, okay, this link. By default, we use 5-tuple hash function that includes source IP, destination IP, source layer 4 port, and destination layer 4 port. And that can be either a TCP or UDP. And on top of that, we also use VLAN ID to help us with the picking one of the available paths. Now, if you need to figure out what path a given traffic with particular set of values would take, you can use this command, show FabricPath load balance unicast, and it's going to tell you which of the links it's going to pick. Now, let's move to the second part of the control plane, multi-destination trees. Remember, I mentioned we need trees to constrain broadcast traffic to a particular loop-free topology. So it goes a step beyond that. Not only it's broadcast, it's something we refer to as BUM traffic, BUM traffic. You might have heard this term before. And it stands for broadcast, unknown unicast, and multicast. So this BUM traffic is always constrained to tree topology. Now, you may say, wait a second, tree, what about all of those redundant paths in the network? So that's why we give you 2 trees by default. You have multi-destination tree 1, and you have multi-destination tree 2. And these trees are identified using F-tag, forwarding tag in the network. There's a couple more slides in this presentation that talk more about this. So what happens here is, because it's a tree, we need to elect a root. So root is elected in the network, and from that root, we build the tree. And by default, there are 2 roots that are elected. Some may say, hang on a second. So you're telling me trees, roots, it sounds like spanning tree, doesn't it? But the truth is, it's more like IP multicast routing. Remember, in spanning tree, or in even in VPC, right, that has spanning tree as an underlay mechanism, we use tree topology for all kind of traffic, for unicast and BUM traffic. In FabricPath, we use trees only for BUM traffic. Unicast is always forwarded using shortest path. Now, control plane, and we will talk about this. Control plane further prunes the multi-destination tree based on some of the information that the FabricPath nodes exchange with each other. So it becomes very efficient in terms of layer 2 BUM traffic forwarding in the fabric. Great. So here's the best practice. identify routes in the network, meaning hard code them to some device. Actually, you should hard code 3 devices: primary, secondary, and tertiary. And the reason for that is primary route will be used to build multi-destination tree 1, secondary will be used to build multi-destination tree 2, and tertiary will just sit there and wait till one of these guys fails. And if it fails, you will have a control over how the new tree or the failover tree will be rebuilt. So why would we want to do this? 2 reasons. First and foremost, it's simple troubleshooting. You will always know that that is my route, and all the multi-destination traffic has to go through that route, or it has to go along the tree which is rooted at that node. Now, the second thing is we will optimize how multi-destination frames are forwarded through the fabric. Meaning, if, for example, if you leave at its fate itself FabricPath to figure out who should be the root, then FabricPath may just simply say, okay, I think this leaf needs to be a root. And because leaf is not centrally located, then it's going to have to attract all the traffic and be the root for the multi-destination tree. Not the best thing. So simple and short, best practice, hard code your trees, hard code your roots at the spine layer. All right, now control plane, we talked about 2 things, right? And now data plane. In data plane, we have 3 parts. But before I go there, do you have any questions on control plane? On multi-destination trees or anything else? No? Okay, question. Okay, the question is what's the minimum number of spines can you have in a fabric? The minimum is you can have 1. You can interconnect all of your spine, all of your leaf nodes through spine, if you need to have spine. But the truth is, because this is a link state protocol, we don't really restrict what topology you should use. We give you recommendation that, hey, if you want this deterministic behavior, you need to have spine. But if you don't, we actually have many customers who deviate from this rule. Of course, we tell them, look, this is not the best practice, but if you decide to do this because you have specific need for that, you can do it. It looks very, how can I say it, organic, the topology, right? It's not going through spine. But if you're building a typical design, you can build 2 spines at least, and you can go up to 16 spines if you decide to do so for very wide, flat layer 2 domains. Any other questions? Okay. Oh, yeah, go ahead. Okay, the question is the spine Nexus 5K and the leaf is the 2K? Spine or leaf is one of the FabricPath capable hardware switches. It's either Nexus 5K or Nexus 7K with F3 line cards. Fabric extender is not considered a leaf or spine, or it's a fabric extender. It's simply a port to some extent, and I'm sure Nexus 2000 product management will not approve this message, but it's a port multiplexer. You take one port on the leaf node, and you say, okay, now instead of having that one non-oversubscribed port on the fabric extender, I want to have this oversubscribed number of ports. If that's by design necessary to you, and it looks like a lot of customers, huge number of customers are doing this, then sure. I think there was a question in the back as well. Yes?
So what would you put, if you have a design where you have 2 spines, right, what would you put tertiary?
Okay, that's a very good question. The question is, if you have 2 spines, what would you configure as a tertiary multi-destination tree root? The answer is, if you only have 2 spines and everything else is leaf, then you will need to pick one of the guys to be blamed in case one of the other fails, right? And it's going to be one of the leaf nodes. As we will see later, there are some design considerations where you can have your gateway in a centralized location. So if I were doing this, I'd probably put my multi-destination tree root, the tertiary, on my border leaf. But we'll talk about this a little later. Let me take this question first, and then I'll get back to you. Sure, go ahead, please.
I have heard of the 9300 switch described as a leaf of the 95s. They don't support FabricPath.
Okay, that's a very good question. So question is, Nexus 9300 and 9500 are referred to as leaf and spine. Do they support FabricPath? No. The FabricPath hardware forwarding support only exists in Nexus 5K, Nexus 6K, and Nexus 7000. And then you can attach Fabric Extender to one of the leaf nodes. Okay, and you had a question.
Do you need a connection between the spine?
Okay.
Also, do you need a connection between the leaf?
Okay. Okay, the question is, do you need connection between spines and do you need connection between leaf? So hold that question. I will cover a lot of details how you can interconnect, but right now I can tell you that you can, we don't restrict you, but there probably would be a reason why you're doing that. Okay. Yes, question. Okay, question is FabricPath follows Trill? Is it an open standard? The answer is FabricPath is not open standard. However, it has a lot of overlap with what Trill is doing. I would say in the FabricPath we have a lot more capabilities in comparison to the Trill. And the hardware that we have is Trill capable, meaning it's a matter of creating a software that would work as a Trill. And today, unfortunately, there is no one sort of agreed upon data plane and the control plane for Trill. Vendors that use Trill, they have their own implementation and flavors. And I think there was one more question there.
So we were told that Cisco is no longer developing FabricPath. Is that true? Or?
Okay, the question is, Cisco is no longer maintaining the developing FabricPath, it's only maintenance. Let me tell you, the short answer is we do have a lot of development and feature improvements with FabricPath. And the testament to that is the new code that's coming up really soon on the Nexus 7000, where we will be supporting things like BFD, bidirectional failure detection. We're improving on some of the things in terms of the Anycast HSRP, as I will tell you later. And also, FabricPath is a baseline, an underlay protocol for one of our offerings in terms of the control plane-based fabric. So you may have heard that we have ability to use FabricPath with segment ID and multi-protocol BGP as one integrated control plane-based fabric. So from that regards, I hope that answers your question. All right, so yeah, one last question and then let's move on to the data plane.
What is the best design to move with the SVIs? On the border leaf or on the spines?
All right, the question is, what's the best recommended design when it comes to configuration of the SVIs, the interface VLAN? I'll talk more about that later. Okay. All right, the data plane. Data plane consists of three key elements. It's the MAC address table, it's the switch table, and it's also multi-destination table. MAC address table is where you have a piece of hardware, right, inside in the forwarding engine of the switch. And it contains the record that says, here is the MAC address, and this is the egress interface. Actually, next slide will show you more about that. So let me just tell you right now that MAC address table just says, this is the MAC, and this is the next hop. Or this is the MAC, and this is the remote switch ID. Now, switch table is a piece of hardware, right? It's a table in hardware that performs the lookup for the destination switch ID. So it says, okay, I need to figure out which egress interface I need to forward the traffic out. And to that, I look into my switch table, and that drives my egress interface. And finally, multi-destination table is a hardware table that runs the hash function to select the tree, and then further identifies which interfaces the traffic has to go out of. So those three elements, let's look into them one by one. So FabricPath MAC table. So all of the lookups in the FabricPath when it comes to MAC addresses happens on the ingress into the fabric, on the edge devices. So say, for example, I have a leaf node, and when workload connects to it, and it needs to send traffic to some other workload in the fabric, the lookup for the MAC address destination will happen on the ingress switch on chip, or ingress switch. So lookup results identifies the output interface out of that switch. And this is what MAC address table looks like. Here you see at the top, you see in VLAN 100, I have MAC address A, and it points to the local interface, Ethernet 2/13. However, I also have MAC address B and MAC address C that point out, instead of the egress interface, they're pointing towards the switch ID. So now I know, okay, if I have this MAC, I need to route traffic through my FabricPath network, or actually switch my traffic through network, towards that destination switch ID. So we call them local MAC entry and remote MAC entry.
Those last two numbers, is that the remote port on the switch?
Okay, the question is, those last numbers here, what are they? Is it remote port on the destination switch? So there's some logic built into this switch ID and sub-switch ID and LID, link ID, right, that may actually, in some cases, drive the destination link interface of the remote. But in majority of cases, we rely on the switch ID for forwarding decisions. Now, let's have a look. We're talking about switch ID. We're talking about F tag or fabric forwarding tag, etc. What does the frame look like? What does encapsulation look like? And this is what it does. We take the original classical Ethernet frame that does have .1Q tag. Actually, it may not have the .1Q tag, but if it does, we just copy it. And then we encapsulate the frame into FabricPath encapsulation. If you open Wireshark, this sniffer tool, you will realize that it looks like Mac in Mac. And that's not very far from true. The only difference is that we do not treat the MAC, this 48-bit field as a MAC address. We rather parse it further and treat those fields separately. There are two fields that are of most interest to us today, are the switch ID and as well as F tag, forwarding tag. Switch ID is what identifies which switch ID is coming from and which switch ID is going to. And forwarding tag, F tag, identifies the unique topology for unicast or multi-destination tree for BOM traffic. So F tag is a little bit overloaded value there, identifier. It can identify both the path or the topology within the fabric for the unicast forwarding, but as well as it can identify the multi-destination tree. Remember, we saw two of them, so there actually can be more than two trees in the topology. And it uniquely identifies which of the trees a given frame must be constrained to. Yes, question?
What do you mean with the unicast topology? Is that the traffic load channel decision you do, or what does that
Okay.
identify?
Let me rephrase question and correct me if I'm wrong here. The question is, what does unicast topology mean? And it simply means, there will be in design section, I will cover this in a little bit more details, but it simply means that your entire FabricPath domain can be split into topologies. And topology will be placed where your multi-destination traffic is restrained to. But also it serves the purpose of separating or sub-segmenting which VLANs may exist in one topology or the other. And we'll talk about this in the design. Thank you for the question. So, FabricPath switch ID. What is it? FabricPath switch ID is an identifier which is unique in the FabricPath network, and it is automatically gets assigned to a given switch. Optionally, we give dials and knobs in configuration for administrators to hard code the switch ID. Now, if there's overlap in dynamically chosen switch IDs, the FabricPath ISIS, inside FabricPath, there's a mechanism that identifies the conflict and resolves it by shutting down the violating node or not letting it initialize. So switch ID exists in both the outer MAC address and inner MAC address, as you saw on the encapsulation. All right. If you are, and this is very important, if you are deploying switch IDs, or when you're deploying the FabricPath, it is best practice to hard code your switch IDs. Why? If you hard coded it, then you know exactly that, hey, look, this given switch is always switch ID, let's say 100, and the other switch is 200. But if you keep it dynamic, then it may become whatever. It just FabricPath just randomly picks the number and verifies that there's no overlap, and it just uses that. So use it for simplicity to make your life simpler when you operate and troubleshoot the network. There are some accepted best practices our customers use today. Some customers follow this thoroughly and strictly. Some others say, you know what, we'll manage it ourselves. But here are the best practices. For spine nodes, use 2-digit switch ID. For leaf node, use 3-digit switch ID. And for virtual switch ID, for example, for VPC Plus or for Anycast HSRP, use 4-digit switch ID. And etc. You can further work your way through the identifying what IDs and what pairs of IDs to pick. FabricPath forwarding tag, F tag. As I mentioned before, F tag is an ID that uniquely is assigned to a given multi-destination tree. So why do we need it? When our traffic, multi-destination traffic, for example, broadcast, unknown unicast, or multicast, comes into the fabric, we will assign that frame to a given multi-destination tree. And throughout the network, it will be constrained to that tree. So while you're in the network, in FabricPath network, you cannot hop multi-destination tree from one to the other. You will be constrained to that. And that is what guarantees loop-free topology for BUM traffic. Now, as I mentioned earlier, it's an overloaded value, identifies topologies and multi-destination trees. And it may actually answer more question to, there was a question on topologies, right?
Would you say that the fact is only used for, or was it just in multi-destination tree that was only used for one traffic? But now it says that for unicast packet, we actually identify all of them.
Yeah, I mentioned this earlier, right? So the question is, so what is it used for? It's used for two things: to identify multi-destination tree using F tag, or identify topology if it's a unicast frame. Meaning, if you have unicast frame in the fabric, it will have F tag in there. And what's the purpose of that F tag in the frame? Is to identify topology. If you have multi-destination frame, you will have F tag there as well, but the purpose is slightly different. It is to identify the tree to which that given multi-destination frame must be constrained to. All right. So what about VLANs in the FabricPath? Well, VLANs are very much relevant here. A lot, very relevant, I'd say. So every frame inside the FabricPath fabric has .1Q tag, every one of them. Even if on ingress you didn't have tag, if it was an access port or you had the trunk native, in Fabric you will still tag them. Now, VLANs are used to make sure that the multi-destination traffic is supposed to arrive to the switch or not. So for example, if a given switch receives a multi-destination frame, and that frame belongs to VLAN A, some VLAN A, and that switch that received it doesn't have VLAN A configured, it's going to drop it. So the recommendation here is configure all VLANs on all FabricPath switches within a given topology. There are some scenarios where you can deviate from this rule, and we will talk about that more, but you should be careful when you do that. Did you have a question?
Is there going to be a deployment mechanism built at some point?
Okay, I think I know what you're talking about. The question is there going to be a deployment mechanism? So I guess you're referring to something like VTP.
Something more stable, yes.
Okay, so at this point right now, we do not have VTP or protocol alike within the FabricPath, but it's on our long-term roadmap. So we can chat about this after the session if you're interested. Okay. So just make sure that you can configure all VLANs on all switches. If you do not, then you must know why you're doing this. And there are reasons. For example, let me give you one example. There's a mode of operation of FabricPath node, which is called transit mode. And when FabricPath node is in transit, it is, first of all, most probably is a spine, meaning it wouldn't work in any other scenario. And if it's a transit node and it's a spine, the reason why you would do that is if you have very large number of VLANs and huge number of multicast traffic in the fabric and things like that. Now, in transit node, FabricPath, in transit mode, FabricPath node only has one VLAN. But that's more of an exception from the rules. And if you do that, you will most probably be looking into massive deployment. So unless it's a massive deployment, then probably you shouldn't do that. What about quality of service in the fabric? How many of you are doing QoS in their networks? Wow. I'd say 60%. So QoS inside the data center fabric with the FabricPath is still possible. The FabricPath hardware is, so Nexus 5K, Nexus 7Ks are designated to work with the encapsulation of the FabricPath. And inside the FabricPath encap, we carry .1q tag. Inside .1q, we have a class of service value. And if we're carrying IP traffic, we also have DSCP values there. So hardware can do various operations, and they're listed right here. What we can do in terms of queuing, matching, or set, et cetera, right? So there are various capabilities that exist, and we can operate and perform QoS operations on FabricPath frames. Okay, now let's put it all together. We have host A and host B in the fabric, and the fabric consists of 4 spines and 3 leaves. On the spines, we have S10, S20, S30, and S40. And on the leaf nodes, we have S100, S200, and S300. We have 2 workloads, host A and host B, with their respective MAC addresses attached to the fabric. Now, host A wants to talk to host B. What happens? Well, what happens in the normal Ethernet? A ARPs for B. Says, I know the IP of B, but I do not know MAC. So it forwards out the broadcast ARP frame. And at this point, on ingress into the fabric, our switch 100 will learn source MAC address of the host A. So it will create an entry. A is local, Ethernet 1/13. Then it will perform a hash, calculate hash, on the header. And because it's a broadcast, we will constrain that frame to multi-destination tree. In this case, we picked multi-destination tree 1. And currently, for that multi-destination tree 1, we only have one port channel, one interface, outgoing interface. So that's what we will do. We will forward out that frame. And here on the spine node, we will do the same thing. We will now need to look up only within multi-destination tree 1. Remember, on ingress source switch S100 already constrained the frame to MDT1, so we will not hop any multi-destination trees. We will stick to that. Spine S10 will make a lookup and see that, okay, as port channel 100 is ingress, so I cannot forward it out, right? Otherwise, it's just going to create loop. So I'm going to have to forward out of all my other interfaces that are part of that multi-destination tree. And so it will forward it out to the other switches. The destination switch 300 will actually perform exact same operations. So it will look it up in the F tag and forward it out to everywhere else. But it will also decapsulate and locally send to host B. Why? Because it sees that there's somebody configured with the VLAN where the multi-destination traffic is coming from. So it's going to forward locally. But at this point, look, we didn't learn the source MAC address. And this is the key difference that you will see when compared to classical Ethernet. In Ethernet, you will learn MAC address, source MAC address, regardless. You receive the frame, you learn the MAC address. Here, we don't. All right, so after ARP request, this is what our MAC addresses look like. S100 has the source MAC of A. Spines have nothing. We do not learn MACs on spine unless there's an SVI, but it's a different discussion. And S300, we don't have anything. Excuse me. Now, question. We talked about unicast switch IDs, meaning if one guy is talking to the other guy in the network, then it's going to be from switch ID to switch ID. What if I have one guy talking to many? What is going to be the switch ID? Here's a set of rules that we use. Multicast MAC is copied from inner MAC to the outer MAC. Oops, excuse me. Why did I do that? Let me get back. Yep. Multicast is the same thing, and broadcast is the same thing. We just copy all FFFF bits to the outer MAC. For unknown unicast, however, there is special case. We use reserved MAC address. We call it MC1, and you can see what that MAC address is. So if any switch in the fabric sees this MAC address in the outer header, it will know that it is unknown unicast. And it will again perform the hash and distribution along the FabricPath F tag. All right, so let's see what the reply looked like. Our host B will send unicast reply back to A. But look, at this point, the switch S300 will say, do I know how to get to A? And it doesn't. This is what we call unknown unicast. Is when you have unicast MAC in the frame, but you don't know what to do with that unicast MAC. So in classical Ethernet, you just flood it everywhere. Here, we don't want to flood it. We want to constrain it to particular tree topology. And that's what exactly that happens. We run the hash function, we perform a lookup, and then we forward it out to the fabric. So eventually, it reaches the spines in the S100, where we will say, all right, so I think it's coming from port F. It looks like it's coming from FTAG1. So, and there's only one port channel, and that port channel was used to ingress this frame. So I'm not going to forward it any further. At the same time, I will look up inside and say, look, the frame is destined to a MAC address that I already know. It's locally connected. And this is only the case here when we will actually learn the source MAC. See, we actually are now having the conversation between two hosts, host A and host B. And in that case, we will learn both the source MAC address, and we will copy the switch ID from the header. So now we know that B is attached to switch ID 300. At the end of the ARP reply, this is what our MAC address tables look like. Switch 100 knows both MACs, local A and remote B. Switch 300 only knows local B MAC address. Then we can say, wait a second, so I just said, remember, conversation. So this is what we call conversational learning. The conversational learning is the following set of rules. New MAC learns are performed on unicast frames only if you know the destination, if you learn the destination MAC locally, right? And edge switches need to learn those, and they do, because hosts are typically chatty, so they start sending GARPs and whatnot, and local MAC address gets populated. So if somebody talks to local MAC address, the source MAC of that frame will get learned as well. Now, this came up a lot with our customers. Be aware of the devices that talk to everybody in the network. For example, if it's a filer server, if it's a domain server or something like that, or it's a default gateway, then every single MAC in the network will be talking to that device. So you would have to learn every single MAC on that device attached to the default gateway or file server, etc. Question? Yes, go ahead. There's a question. Okay. I'm sorry, I didn't understand the question.
So whatever VNAT we use, right? Let's say that we're both on VNAT 20, right? So we configure including the leaf, which is pointing down to the server, or whatever device. Is that true?
Yes. So the question is, on the previous example, let's say both host A and host B are in the same VLAN. Does that mean that we configure VLAN on both the switch 100 and switch 300? Yes, the answer is yes. We can. Yes. So the question is, how is VLAN configured? The answer is VLAN on FabricPath node can be in two modes. It's either classical Ethernet mode or FabricPath mode. If it's classical Ethernet mode, then frame that arrives in that mode VLAN not going to be forwarded through the FabricPath. If VLAN is configured as FabricPath mode, then this is the only case when we will forward traffic through FabricPath. And the links is what is configured differently. For example, link may be configured as a FabricPath core port, so you would say switch port mode FabricPath, or links may be configured as host port, for example, access or trunk port. So I hope that answers your question. If there's more questions, we can chat afterwards. Okay? Good. So who knows, is MAC address learning in FabricPath software or hardware? Okay, was there an answer? Okay, yes, it's a hardware. Binding, there's two things, right? Binding of MAC addresses to switch IDs happens in hardware. And then the conversational learning logic is also happens in hardware. So what happens if host moves? For example, we did the vMotion or hot migration or cold migration, but our MAC and ARP entry didn't time out. So what happens? There's further rules that are refined for the conversational learning, right? So we do not learn new MAC addresses on broadcast, but we do learn MAC addresses. We update MAC addresses if the MAC is already known locally. So for example, if a virtual machine or workload moves from one switch to the other switch, then the FabricPath will handle this host move exactly like it handles in the classical Ethernet. It will be responsibility of host that moved from one place to the other to tell the fabric, to tell the network that they had moved. And what are those tools? It's either reverse ARP or gratuitous ARP or anything else that basically speaks up either by virtual machine itself or by the hypervisor or whatever the software that runs and facilitates that move from one place to the other. If that broadcast now arrives and now broadcast frame has a different switch ID, then we will simply update the entry. So what happens if the MAC table capacity is exceeded? And there's simple answer, exactly same thing as traditional Ethernet. If MAC table lookup is based on the hash function. So on ingress, we will look up in a table using hash function. So if hash collision happens on the new source MAC, meaning we receive a frame and we need to learn new source MAC. And at that moment, if we get a hash collision, then we simply don't learn the MAC, the source MAC. If the destination MAC lookup returns miss, then we will forward it out as an unknown unicast. Now, putting it all together back, we had ARP request, we had ARP reply, and now unicast data. They both of the hosts know of each other. At this point, MAC address A, well, host A will send traffic to B, and switch 100 already knows destination MAC B, and it says it's a remote entry. So I need to forward it out to the destination switch ID 300. So this is now unicast traffic. On ingress, our S100 will perform a routing lookup. And routing lookup will say that S300 is reachable out of these egress interfaces, port channel 10, 20, 30, and 40. At this moment, we will perform the ECMP equal cost multipath hash function to pick one of the paths. Yeah, sorry, thank you. And then it goes to the spine. On the spine node, we will only look at the switch ID. We will not look into MAC address. And switch ID says destination switch ID S300. All right, so forward it out. Once that frame arrives to S300, S300 performs lookup for the destination MAC, and it also sees that, look, I am the destination switch. So because I'm the destination switch, I need to make a MAC lookup. It does MAC lookup. It finds the entry B, and because it finds the entry locally, it learns the source MAC. So now we have complete picture. We have A, B, and we have A, B. After both hosts ARPed request, reply, and communication, we now have a fully featured conversation between two hosts. This is when you will have both MACs on switch 100 and switch 300. Okay, any questions on the unicast forwarding? Because next step would be multicast forwarding. Yes, question. Okay, so question is, there are two questions actually. Where are the multi-destination trees rooted here on this topology? And the second question is, did you configure as VLAN 100 on all of these ports, right? That's the question? Okay, so the multi-destination trees, there was a slide that was showing it, are rooted as S10 and S40. So that's why the ARP request reply and any other broadcast, unicast, multicast traffic, bump traffic, will be restrained to one of those trees. Which one to pick, we will figure out by hash function. Once we picked it, we will constrain to that tree. Now, that's the first question. And the second question is, when you configure FabricPath switch, you will put on the link between the leaf and spine, these links will be configured as switch port mode FabricPath. And that means that it's a trunk FabricPath. In that case, you do not need to configure one by one allowed VLAN. You do not need to do that. Any VLAN on the switch that is configured as FabricPath mode VLAN will be trunked on that port. So that's why all 4 ports towards spines will have capability to forward traffic along VLAN 100 in unicast. But you will only pick one of the paths for a given conversation. Remember, let's say if I have two hosts talking to each other, and if they're using all exact same values in terms of source IP, destination IP, source port, destination port, and VLAN, and it never changes, we do not want to reorder that traffic. We don't want to just sprinkle it across all links. We want to keep it across one path because that would guarantee consistent bandwidth and consistent latency. If we start sprinkling it all over the place, then on the other side, it may arrive out of order. So we do not want to do that. That's why, even with equal cost multipathing, it's like an IP layer 3 routing. You do ECMP hash, and you pick only one path. If there's different conversation between these two hosts, and it uses different values in that match the hash algorithm, right? Then we will pick another, perhaps, right? And if you have enough of the diversity in terms of these values between two given hosts, then you will be able to leverage all 4, right? It's just like in layer 3 routing.
Okay, I understood that, but in the topology tree that you showed, there was only one switch path out of switch 100 to switch 10.
Mm-hmm.
Then it came down to switch 300 that had forwarding paths for that same VLAN up to all spines.
Okay, I'm afraid, let me table this discussion. We can talk about this later because I just don't want to go down there. Yeah. All right. All right, so we talked about unicast. We talked about ARP, request, reply, conversation. Let's talk about multicast now. What we do in FabricPath, we take advantage of 2 things. First of all, it's IGMP snooping. IGMP snooping runs on edge switches, and it is used to track interest of a given workload in particular multicast group. So for example, if workload sends IGMP join, then we're going to create a state locally on that edge switch that says that interface is outgoing interface, and it's interested. And also, if there's a report, the leave or something, IGMP leave, then we're going to say, okay, withdraw, no longer needed. That's one part, IGMP snooping. The second part is, the GM LSPs. This is part where FabricPath ISIS comes into play. Once you have IGMP learn the interest in particular multicast group of a particular port, then FabricPath takes this state and sends out floods throughout the network. Oops, excuse me. Let me go back. And it floods throughout the network the GM LSPs. It's essentially group membership LSP. It's the ISIS update that says, I am the switch and I am interested in particular multicast group. So all of these GM LSPs are flooded throughout the network, and that way you can get, you can build a state, forwarding state for multicast in FabricPath. Now, the next slide shows you CLI output, where on the first show command shows you the IGMP snooping. So you create, for example, for this group, 239.0.0.1 in VLAN 10, we have interest on Ethernet 1/13. That's outgoing interface. Now, GMLSPs, and by the way, there's two receivers, receiver G1 on switch 100 and receiver G1 on switch 200. So we will, on switch 100, we will learn that via GMLSPs, via FabricPath ISIS, we will learn that there is switch ID 200 that is also interested in this multicast group. Then we take the two, we bundle them, and this is when we create M2 rib, or show FabricPath M route. If you're familiar with the layer 3 multicast, there's a notion of M3 rib, multicast layer 3 routing information base. Here we have what we call M2 rib, multicast layer 2 routing information base. And essentially it says, from perspective of S100, I have two items that are interested in this particular multicast group. It's local port, Ethernet 1/13, and remote switch ID. So what we can do is we can take and further optimize our multicast, IP multicast forwarding within the fabric. How do we do it? We already have multi-destination tree 1, right? And it constrains multi-destination traffic to that particular tree topology. But we would like to avoid unnecessary flood of traffic to those switches that just don't want it. They never express interest in that particular multicast group. And that's why we will create a pruned tree. So we will overlay pruned tree on top of our tree 1, and we will do the same thing with the tree 2. We will take our pruned tree for particular multicast group and overlay on top of our tree 2. Now, I have, for a given multicast group, G1, I have two trees, or two pruned trees that I can use. So this is the way how we improve the efficiency of multicast forwarding within the fabric. Here you see that on ingress into the switch 300, I have source now sending traffic to group 1. And on ingress, I will perform a lookup. I will perform a hash. I will drive the hash function to pick one of the trees, multi-destination tree 1 or 2. Once I picked it, then I will see what frames, what interfaces I should be forwarding out of to. And this table right here, here, I only know, I will only use interfaces that are part of the pruned tree, because I know that this is group 1, and I just don't want to flood it into the whole multi-destination tree, but rather into the pruned tree. Then I will flood it towards my spine. On the, on the spine level, I receive the frame here, and this is what I do. On spine, I will know that, okay, it's the tree 1 that it arrived from. So on spine, I no longer do hash. I'm already constrained to tree 1. But I will then say, okay, I have the port channel 4 and port channel 5, out of which I need to forward that multicast traffic. and so I will. My switch 100 and switch 200 will receive this frame, and because they have locally maintained IGMP snooping for the local port, they will forward out that traffic to the receivers. So this way, we did not have to flood our multicast or forwarded multicast in layer 2 network to those nodes that are not interested. We only forwarded to those guys and switches that expressed explicit interest in a particular multicast group. So best practices then go into the VPC Plus. So let me pause here for a second and ask you any questions on multicast. Yes, there's a question. Group membership, GM, group membership. I believe it stands for Link State PDU. So it's the ISIS terminology. Okay. By the way, the question was what GMLSP stand for. Yes, there's more questions.
Does that mean for every single active multicast group in the network, there are 2 tree states being created on every single switch in the development, despite whether or not, so I guess transit switch is still going to have specific tree states created for each multicast?
Okay, question is, does that mean that every single multicast group drives the creation of multicast, 2 multicast states on each switch in the topology? The answer is, we already have multi-destination trees, right? What we do create is a pruned tree. And for that pruned tree, yes, we create a state in the hardware so that when our multicast arrives, we know, let's say it's arriving in particular VLAN. If that VLAN exists, then we will make a lookup and drive the whole thing that we just looked through. So yes, to your question, we do maintain those states. Yes, question.
So does that do away with dense mode and sparse mode and so on and so forth multicast, or do you still need that running somewhere?
Okay, question is, does this deal with the dense mode and sparse mode, etc.? What dense mode and sparse mode is in multicast routing, and what we're here talking about is a layer 2 multicast forwarding. So if you need to perform dense mode or sparse mode, that's going to be on the edge of the network where you start routing and hand off of the routing information using multicast routing protocol. This is when you will need that dense mode or sparse mode. It's after the routing hop. Within layer 2, we need to maintain. In a traditional environment, and this is interesting, thank you very much for bringing this up. In traditional environment, we only use IGMP snooping, right? So they leverage this. Here, apart from IGMP snooping, we use GMLSP and FabricPath, and that allows us to optimize our multicast forwarding states in hardware. All right, changing gears. Let's talk about VPC Plus, Virtual Port Channel Plus. There are primarily 2 cases why you would want to use this. And first of all, it's for dual homing of your devices. You can either take your classical Ethernet host, and if it has capability to drive port channel, let's say from the server, you can just bundle those links on the host into port channel and connect to the 2 nodes running VPC virtual port channel, right? The other case is if you have a spanning tree protocol running on the switch and you need to plug it in to your FabricPath fabric. In that case, the most stable way to plug it in is using port channel because you are provisioning 2 redundant paths or like 1 + 1 redundant path bundle into port channel. And all is needed from the attached device point of view is just ability to bundle traffic. Either static port channel on, or dynamic using protocol LACP. Now, this removes a lot of complexity from that scenario when we need to interconnect spanning tree devices. We know we do not forward BPDUs into the fabric unless you specifically configure that. By default, it doesn't get propagated. And also, topology change notifications do not propagate through the fabric. So, here we have sample device, let's call it a Catalyst 6500 that is dual home to our spine S10 and S20 to these 2 FabricPath switches. Here we will need to provision the VPC peer link for the VPC Plus. We will also need to provision and ensure that the VLANs that are used on this port channel are FabricPath mode VLANs. So again, this guy doesn't need to know anything about VPC. All it does is the port channel or LACP, static or dynamic. from the logical topology perspective, this Catalyst 6500 now will be hiding or connected behind a virtual switch. What does that mean? Both the switch ID 10 and switch ID 20, they are both symmetrically configured with the same virtual switch ID. Now, we call it an emulated switch ID. What does that mean? It means that if my workload attached to Mac C needs to talk to workload attached to Mac A, the switch ID S200 will think or will perceive that the Mac A is attached to one switch, not two switches. It wouldn't show up as if it was attached to S10 or S20. It would show up as if it was attached to S1000. And because of that, if we have multiple paths towards the S1000, we can leverage and take advantage of those multiple paths. Now, if you are, okay, so S1000 and multiple paths, right? There was a slide for this. Good. Now, even if you're not using dual homing to FabricPath switches, you can still take advantage of VPC Plus for active HSRP. So what does that mean? If I configure VPC peerlink here, and I have SVIs, virtual interfaces, and I'm running HSRP, both of the nodes will become active HSRP forwarders. You don't have to do active standby, listen. You can do active forwarder. From control plane, they will look like active standby, but from forwarding perspective, they both will be able to forward traffic. And because they advertise this thing, virtual port channel plus VPC plus virtual switch ID to virtual MAC of the HSRP mapping, all of the leaf nodes will have a mapping that says HSRP virtual MAC is reachable through S1000. And to get to S1000, you need to go through port channel 1 and 2. So this way, if you need to go to the default gateway, you don't need to go to S10 or S20. You can just go to one thing, S1000. Logically, it looks like this. Your router, HSRP MAC, is behind S1000. Yes, question?
For this scenario, or any HSRP, do you really have FabricPath in place?
Say again, please?
VPC.
I'm sorry, I couldn't hear you.
For HSRP active.
Mm-hmm.
In my opinion, I think is VPC already taking care of that. Do you really need to have FabricPath for that?
So if you do VPC, then, okay, so the question is, do you need FabricPath to do the active HSRP, or do you need FabricPath? With the VPC and classical Ethernet, you do have active HSRP indeed, but all of the topology or all of the fabric underlie is still driven by the spanning tree protocol. So the goal idea here is to get rid of that instability that may get introduced by the spanning tree protocol. And if you choose to do so, you can leverage exact same feature as we have in VPC Plus. So you're right on that regard. So, yes, question?
Does a VPC Plus have to be plugged into the spine, or can it be plugged into the leaf?
We will talk, okay, the question is, does VPC Plus have to be plugged in at spine or leaf? We'll talk about that in the design part. Now, if two-way active default gateway is not enough for your particular environment, we give you ability to do four-way. And that's what we call Anycast HSRP. With Anycast HSRP, I have an ability to emulate the same switch ID with the virtual MAC of HSRP on up to 4 devices. So from software perspective, it's possible to do even more. What we validated is 4 active devices. So your routing table on a leaf would look like this. S1000 is reachable out of port channel 1, 2, 3, and 4. And I would like to spend a little more time on this slide. I'm sure during CiscoLive, this is just the beginning, right? You will hear more about control plane-based fabrics. So things like VXLAN EVPN or fabrics with the multi-protocol BGP that is used for end-host reachability distribution. So there's one thing that exists there. It's called Anycast Distributed Gateway. And so as familiar or as similar as it sounds to Anycast HSRP, those are different things. And some may ask, why would you have Anycast HSRP with FabricPath if you can have Anycast distributed gateway in control plane-based fabrics? And the answer is they solve different things. They solve different problems, right? Now, the Anycast distributed gateway requires some level of automation and orchestration in the network that is provided by external controller. And that automation and orchestration is required because we need scoped configuration. Excuse me. The scoping of the configuration is absolutely required because we have this distributed Anycast gateway. If you're interested, I will actually be talking about more of this feature tomorrow. Actually, I have a session, BRKDCT 2456. And with Anycast HSRP, what we're achieving is a simply incremental improvement over what we have with, let's say, spanning tree or VPC Plus, right? Now, unlike VPC Plus, we have four-way default gateway, which gives you immediately two benefits. Immediate benefit. One is it's higher available, right? HA, you're increasing HA. What does that mean? Now you have 4 nodes, and if one of them goes out, you still have 75% of your gateways, which is much better than you losing half of everything you have on the default gateway. That's one, HA. And the second, you have more bandwidth. Now you have 4-way default gateway, and you can take advantage of 4 times more of the bandwidth. Any questions on Anycast HSRP? Excuse me.
What are the other advantages other than the bandwidth?
High availability. Yeah, the question was, what was the first one? High availability.
All of these are layer 2 connected?
So yes, the question, are they all layer 2 connected? Our spines here are our default gateways. So they host SVIs. And they are used for east-west. They are used for inter-VLAN routing between the VLANs in the fabric. And they are also used for north-south communication. And our leaf nodes are all layer 2 FabricPath. We'll talk a little bit more actually in the next slide. So FabricPath designs. So by now we've finished all of the control plane, data plane components, and how things and states it gets established in unicast, how we drive multicast, and how the control plane interoperates with the data plane in FabricPath. Now I'd like to spend some time to talk about FabricPath designs and what our customers are doing in their data centers. So primarily, there are three designs that we will talk about, and this section is here to help you explore what you can use in terms of design building blocks and how you can use technology. So that's back to your question about multi-topologies, right? How can you put all of that we talked about in use with the specific designs? Not only that, how can these designs meet your requirements for building layer 2 fabric? The assumption here is that we will not be talking about what is better, layer 2 or layer 3. We have already decided that we are building layer 2 fabric, and we answered the question, why layer 2 in data center? Having said that, let's have a look at just high level, the 3 key types of design. Routing at aggregation, routing in centralized location, and also the multipod. Let's start with the first one, routing at aggregation. This is very similar to what you see in the classical, traditional designs. You have layer 2 access, you have layer 2, layer 3 boundary at the aggregation, and you have layer 3 uplinks towards your core. With FabricPath, you can do either this, which you could do with VPC, and you can also do this on the right side with 4-way active default gateway using Anycast HSRP. So some of the highlights here. Within Fabric, for intra-VLAN forwarding, bridging, we will not use any of our SVIs. It will all be FabricPath switched based on switch ID. For inter-VLAN routing within our FabricPath network. We will be routing traffic using SVIs on the aggregation, on the SVIs on the aggregation spines. And for all the north to south and south to north forwarding, we will also use those SVIs. Our access layer is pure layer 2, meaning it only takes care of maintaining the edge information in terms of MAC addresses, the remote MAC addresses, and also on the multicast side in terms of the IGMP and GMLSP when that's necessary. You have an option to use VPC Plus at the access as well. So if you need to dual home your host or dual home your spanning tree switch, you can do that at the access. So 2 spine design, really, and here are the immediate benefits that we get. One of them actually is this guy, removal of STP. This alone got a lot of customers migrating to the FabricPath because they were just tired of FabricPath spanning tree, and they migrated to FabricPath. Now, we give also active-active gateways and VLAN anywhere. This is from numerous customers that I talked with. By far, VLAN anywhere is the biggest deal, one of the biggest deals. Why? Well, they're saying that, look, my application guys, my server guys, they just would like to have this freedom where they put rack mount or blade server somewhere in one of those racks, one of the 50 racks that we have, or however many racks, and they just want to have virtual machine or application in particular VLAN. So do not please restrain me to particular portion of the data center where I can use given VLAN. Give me VLAN anywhere. So this is what provides, the FabricPath here gives you that benefit. Some of the interesting applications that we found over time is the following: topological flexibility. For example, if I have 2 workloads, and this happened, I've seen this at least 4 or 5 times with the customers deploying in the research facilities, where they have multiple database and the analytics server, and both of them were very chatty and using a very, very huge amounts of bandwidth. And they asked us, hey, can I, instead of pumping my traffic through my gateway or through my core aggregation, can I just have local connectivity? They couldn't do it with spanning tree, because spanning tree would block the ports directly attached between leaf nodes. Here, they can do it because we have FabricPath ISAS underlay. It calculates it as the shortest path. You can provision as much bandwidth as you want there. And again, it's either because you have bandwidth or latency requirements. Also, if you're trying to provision layer 4 to 7 services, firewalls, I don't know, tenant edge firewall, east-west firewall, or load balancers, and let's say with source NAT, without source NAT, regardless, exactly same as in your traditional environment. You plug them in here at the aggregation. You can do policy-based routing there, if you will. If you need to, let's say, retain end client visibility, that's all possible here, and it's really easy to do. So that's really the routing, the aggregation. If you need to go beyond 2 gateways, we can give you the same thing with Anycast HSRP. We already talked about the technological or conceptual underlay, how this thing works. One thing I need to mention here is the MAC scalability at the aggregation layer. Remember, these 2 parts, these 2 gateways, or 4 gateways, if you will need to learn all of the MACs in the whole data center, right? Because you're routing at one location at the aggregation. And when you do that, you must provision enough of the MAC address table capacities, right? With the F3 line cards, we have 64,000 MACs. And with the Nexus 5600, if you decide to deploy layer 2, layer 3 boundary on Nexus 5K, we have 32K MACs. However, there's always however. Check this link for the MAC and ARP hardware entries carving, because on Nexus 5600, there's one table that is responsible for both the MACs and ARPs, and it's flexibly can be carved one way or the other. So check out this link. If you have any particular specific requirement, this is just for your reference here. Okay. Yes, go ahead. There's a question.
With controllers for wireless on these devices,
Mhm.
broadcasting are you running an NAP 32,000 or 64,000? Are you having any problems for on an enterprise level with the BYOD stuff?
Mhm.
The wireless controllers are causing people to start to hit their max.
Mhm.
You know, the cam limit.
Okay, so the question is, have we ever seen that when our customers plug in wireless LAN controllers with tens of thousands of MAC addresses behind a given switch, do we see any MAC exhaustion? And the answer is yes, we have seen a couple of cases like that. Yeah, we've seen some cases there, and it was basically due diligence on our side to explain that if you're bringing it's a matter of application, right? If you're bringing the campus connectivity of the wireless into your data center, then you better have good reason why you're putting campus into data center and not behind some core router where it's routed into the data center. So from that regard, yes, we have seen some of that happen, and we have some of the guidelines, and talk to me after the session if you're interested in some specifics. Guidelines how you can scale much better. In fact, there are several white papers in the works to get that out on the public domain at Cisco, right? All right, now that was aggregation, routing and aggregation. Now centralized routing. And this probably seems very familiar to you, but notice that FabricPath is now extended all the way up to core. Another way to look at it is this. This, excuse me, this is when now we have two-tier topology, where first tier is our leaf nodes, and second tier is our spine nodes. But check this out. Our leaf nodes now have something we call a personality. The leaf node may now be a server leaf, where you plug in your servers and appliances and, for example, blade chassis. And you can have a personality of the services or border leaf. And this is how you get out of the domain. And back to question gentleman was asking about, there was a question about spine and leaf. This is where we see spine and leaf, right? Two-tier topology. Excuse me. Now, at the border leaf, you can have plug in your external layer 3 domain towards the core or SP edge. And on the, you can also plug in some services here. For example, if you need to perform your source NAT, no source NAT on load balancer, firewall, etc. All of that can be plugged in there. So some of the highlights here, it's a little bit of a paradigm shift for when compared to the classical traditional designs. And traditional aggregation layer now becomes pure FabricPath switch. All it does, it just forwards traffic from one place to the other based on the switch ID. And in the simplest case, it doesn't even look at MAC addresses at all. It only looks at the source switch, destination switch ID. And by the way, spines and every other FabricPath node in the network looks at the source switch ID. And there is a reason for that. We perform, and I probably should have mentioned it at the technology portion, we perform RPF check, reverse path forwarding. So if we receive a frame that is not supposed to be received on a link where it came from, we're going to drop it, because it means that something may have happened in the transit while the fabric was converging, and it may have arrived from the wrong place. Or somebody's doing some sort of attack or soliciting some the rogue switch IDs or something like that. So here, we really have FabricPath leaf switches as layer 2 server switches, server leaves, connected to spine, and they're, again, pure layer 2. But some others, layer 2, layer 3 boundary switches, those are border leaves. And they are running OSPF or BGP or what have you with external routing domain. We have a pretty large oil and gas company customer who are using this particular design. And they have spines, four-way spines. They have a whole bunch of access server leaves. They're also plugging in appliances, blade chassis, some monitoring tools there. And they're using layer 2, layer 3 boundary at the border leaf. And they're using BGP protocol to interface with the external routing domain. Here, this gives us very interesting flexibility the flexibility in two folds, right? First of all, because this guy now is only doing layer 2 switching, and there's 4 of them, you don't have to put modular chassis here. You can put a lower form factor, high density, 40 gigabit switch, like Nexus 5696Q, right? It has 96 ports. Well, it's a 40 gigabit switch, right? Let's leave it at that. There's different form factors of Nexus 5K. Now, because and we don't really care anymore to the same extent whether it fails or not, because we have 4 of them. If one goes out, we still have 75% of our spine capacity, so it's good. At the same time, if you want to have like advanced features here, for example, on one side, it's FabricPath network. On the other side, you terminate your FabricPath network into SVI, and you are the beginning of the MPLS. So southbound from here would be MPLS network. If you want to do that, we give you that ability as well. So you can integrate your FabricPath directly and interface with MPLS. Now also, okay, next slide. You can run VPC here, and that's back to somebody was asking about where can we use Anycast HSRP or VPC Plus. Here you can run either VPC Plus, or if you decide to have a wider domain, layer 3 domain, you can use Anycast HSRP there as well. All VLANs are available on all leaf switches. So any VLAN anywhere. And on top of that, these SVIs here perform termination of these VLANs. Now remember, if let's say there was a question. Yeah, go ahead. Mm-hmm. No, not the fabrics, one of the nodes, yeah. Mm-hmm. Okay, question. Does hashing function work well with the odd number of next hops? We don't really care. It's a hash function, and it can equally efficiently use odd number or even number, right? Okay. Now, with the centralized routing, if you have intra-VLAN bridging, then you will never go to the border leaf. If you need to go inter-VLAN within Fabric, then you would go to the border leaf. And if you need to go north to south and south to north, then you will again go through the border leaf. So really, question is, why would I use this design when compared to the routing at aggregation? And this is a very popular question. Let me put it this way. It's a very popular question. Why would I use centralized gateway at the border leaf or aggregation? Let's call it a border spine, right? The simplest answer here is the following. If you have a lot of east-west traffic and you never leave the domain, then this is probably one of the most efficient ways to build your data center. If you have a lot of east-west and very little north-south. If you have 50-50, then you don't really care. Of course, if all of your traffic goes through the north-south and almost never goes to east-west, then of course go with the routing at aggregation. But again, if you have sizable or large quantities of north-south traffic, we also give you this ability, where you can dedicate a particular pair or 4 border leaves to act as a default gateway. In this case, you will have some VLANs terminated on this pair and some other VLANs terminated here. So from that regards, we give you that ability, and FabricPath ISIS give you that flexibility how you interconnect things. All VLANs are configured on all access switches. It's just their gateways are either on one pair or the other pair. Now, to make sure that the routing happens across these sets of VLANs consistently, within FabricPath network, we will use transit VLAN, and that transit VLAN will allow us to keep the routing information consistent. Okay, so if you need to go inter-VLAN, interset of VLANs, this is what the routing would look like. You will have to terminate on your SVI, then from SVI route to another set of SVIs and come back into the fabric. Yes, question? How does it figure out? It's a cost. So there's a question, how does it figure out that it should go internally via FabricPath versus the external core router? It's a matter of routing cost. You're going to have probably a better path through internal link because of the link path cost, right, than through external. Or you can manipulate using the policies. Please hold your questions. I need to pick up the pace. We have not a lot of time left, so I'll get back to you. So multi-pod design. This is the third design, and this is really what the gentleman was asking about, the multi-topologies. This is where we address those questions. Really, it's a hybrid of centralized gateway at the border and routing at the aggregation. And the reason why you would want to do this is because, and here's a live example. I worked personally with three customers, right? And there's also, my colleagues and my team worked with numerous of customers who are using this. And let's say, in my case, it was universities, very large universities in the United States. And what they're doing is they have campus. They have multiple buildings. And for each respective portion of the campus, they have a data center portion of it. And what they wanted to do is they wanted to constrain some of the chatty protocols and some of the applications to portion of the fabric. But they didn't want to build 3 different fabrics. So what they did, they built one fabric, and they said, okay, I will have one pod within my FabricPath, or one topology within my FabricPath to host these applications. I will have another pod or FabricPath topology to host different set of applications. And finally, I'll have 3 for the third portion. From the configuration perspective, it translates into the following. You will have set of local or pod-specific VLANs in each of the pods, and you will have DC-wide VLANs, right? So some of those VLANs, they are spread across all of the pods. And this is possible with the FabricPath's multi-topology feature, where the termination, meaning the SVI default gateway for inter-VLAN routing or for north-south traffic routing happens within topology on this aggregation. And for common set of VLANs or DC data center wide VLANs, we terminate those at this location. And internally, they will all maintain this routing adjacency using transit path. Any questions here? All right. Yes.
Okay, you have a data center wide VLAN. You also have some maybe global VLAN.
Mm-hmm.
Okay. So they definitely need some kind of layer 3 to exchange information.
Yes.
How are you going to accomplish that?
So there's the question is, if I have this sort of a solution, right, this set of a setup, then each of the pods locally terminating VLANs with SVIs, but how do you keep routing information consistent across these pods and the centralized core location? The answer is we will use transit VLAN that is only used for routing for this purpose between these pods or across these pods. So I hope that answers your question. There's a question in the back. Okay, that's a very good question. Where are the spine routes, meaning where are the multi-destination tree routes? Because we have topologies now, we have 3 topologies and 1 unique topology, 1 default topology, right, default route. Per each of the topologies, we will calculate multi-destination trees. So you will have 2 trees spreading entire fabric, and that would be multi-destination tree 1 and 2 in topology 0, default topology. In each of the topologies, you will have its own set of multi-destination trees, multi-destination tree 1 and 2, and then here and here. So I hope that answers your question. And of course, you can configure per topology the multi-destination tree root priority so that you can enforce that deterministic behavior. And one more, I guess, last questions here, yeah?
So I'm assuming that the SVI for the hot local VNAS, let's say 1 VNAS 100, 199, exists on the port, right?
It exists on these devices, yes.
Correct. So, but what about the data center wide VNAS, 2000 to 299?
Yeah.
To the SVI?
Okay, so the question is, the VLANs, pod local VLANs are terminated on this aggregation. Where are these data center wide VLANs terminated? They are terminated right here.
You don't have a layer 3 link to the layer 2 router.
See, this is synthetic exercise here, right? In the production, you may have these SVIs on these devices here, right? Because FabricPath may span all the way up here, or as you see, these are layer 3 links. So the layer 3 uplinks from here are just not shown, right? Okay. All right, so we have just a little bit of time for to wrap things up, and here are the key takeaways. So we saw that FabricPath is simple. It's simple in terms of provisioning. It's simple in terms of configuration. There's only a few commands that you need to do to get the FabricPath going in your network. And it integrates scalability of the layer 3 and stability with the benefits of layer 2. It's efficient because we can do equal cost multipathing. We no longer restrain to, let's say, blocked path, right? We don't need to block path. We have FabricPath ISIS. And also, if we have shorter path between devices, FabricPath nodes, we can use that shorter shortest path within FabricPath topology. And it's scalable, right? We saw with the multi-pod topology there, with the multiple topologies feature, you can scale to large fabric and yet keep certain domains contained to a particular portion of the network when you need that specific design requirement there. So from the design perspective, we saw 3 main designs: centralized routing, routing at aggregation, and multi-pod. There's application for each. We have a wide variety of customers from small, medium, and large enterprises deploying a lot of these designs today, and with the respective best practices. And one of the biggest thing, of course, for them is removal of spanning tree and providing of the any VLAN anywhere type of environment. So you have multiple design options there. So as a conclusion, I'd like to thank you for coming today. By now, you should have a thorough understanding of how FabricPath works. And please fill out your online session evaluation. And you can continue your education. I will be in World of Solutions after this session around 4 p.m. today. So you can come by and ask me any other questions. But I'll stick around here as well. So thank you very much for coming today.